What if everything you have ever known, every star, every planet, every galaxy, is only a small bubble inside something far greater? When we look into the night sky, we are not just seeing space, we are looking toward the edge of reality itself. This journey takes us to the boundary beyond which light has never reached us, the edge of the observable universe. The observable universe is not the entire universe. It is only the portion we can see, limited by the finite speed of light. Light travels at an astonishing 299,792 kilometers per second, yet it still requires time, enormous spans of time, to cross the cosmic void. Because the universe is about 13.8 billion years old, light from regions beyond a certain distance simply has not had enough time to reach Earth. This creates a cosmic sphere of visibility with Earth at its center. When we train our telescopes on distant galaxies like GN-Z11, glimpsed as it was just 400 million years after the Big Bang, we are engaging in a form of time travel, observing them as they were billions of years ago, long before our Sun ignited or Earth coalesced from stellar dust. A subtle but profound implication, first rigorously described by cosmologist J. Richard Gott III in his work on cosmic horizons, is that we are not seeing these objects where they are now, but where and how they were when the light began its journey. The universe we perceive is a mosaic of different epochs, a historical archive written in photons. Here lies one of the cosmos's most elegant puzzles. Although the universe is 13.8 billion years old, the radius of the observable universe is approximately 46.5 billion light-years, giving it a diameter of about 93 billion light-years. How can we see light from objects that should be at most 13.8 billion light-years away? The answer lies in the expansion of space itself, a discovery pioneered by Edwin Hubble in the 1920s. Galaxies are not merely moving through a static space. The fabric of space-time is stretching and carrying them apart. Think of dots on an inflating balloon. As the balloon expands, every dot moves away from every other dot. The farther away a galaxy is, the more space there is between us to stretch, and thus the faster it appears to recede. This leads to the counterintuitive reality that at the outer fringes of our observable sphere, galaxies are receding faster than the speed of light relative to us, a result of expanding space, not motion through it. As theoretical physicist Tamara Davis explains in her work on relativistic cosmology, this means light from the most distant galaxies embarked on its journey when the universe was far denser and smaller, fighting against an expanding space to finally reach us today. Light emitted from those regions now will never arrive. This invisible boundary is known as the cosmic horizon or the particle horizon. Beyond it, the universe still exists, but its light is forever beyond our reach due to the accelerating expansion of the universe, a phenomenon confirmed by observations of distant supernovae in the late 1990s by teams led by Saul Perlmutter, Brian Schmidt, and Adam Rees, work for which they won the 2011 Nobel Prize in Physics. No matter how advanced our technology becomes, there are islands of galaxies, perhaps entire cosmic structures, that have already slipped beyond this horizon. The universe places a fundamental limit on what we can know, and over time, as expansion accelerates, more and more of it will vanish from our view, isolating our celestial descendants in an ever-shrinking island of the visible. What do we see when we look to this very edge? We do not see stars or galaxies. Instead, we detect a faint omnidirectional glow, the cosmic microwave background, CMB. This is the ancient afterglow of the Big Bang itself, released about 380,000 years after the universe began, when it had cooled enough for protons and electrons to combine into neutral hydrogen atoms, making the universe transparent for the first time. This radiation, discovered by Arno Penzias and Robert Wilson in 1965, is the oldest fossil we can ever observe. It is a snapshot of the infant universe, a silent echo from the birth of everything. Detailed maps from satellites like COBE, WEMAP, and most recently, the European Space Agency's Planck satellite have turned this faint whisper into a rich data set, revealing the minute temperature fluctuations that are the seeds of all future structure, galaxies and clusters of galaxies. Beyond this luminous edge lies profound mystery. Scientists do not yet know what, if anything, lies beyond the cosmic horizon, but compelling theories suggest our bubble is but a small part of a staggering whole. The prevailing cosmological model, inflation, proposed by physicists like Alan Guth and Andrew Linde, suggests that in the first fractions of a second after the Big Bang, space underwent an exponential expansion. If inflation is eternal, as Linde's chaotic inflation theory proposes, then it may have spawned an infinite multiverse, a vast frothing sea of bubble universes, each with potentially different physical constants and laws. Our entire observable universe would be a single bubble in this endless cosmic foam. Other ideas, such as conformal cyclical cosmology, proposed by Sir Roger Penrose, suggest a more cyclical nature, where the distant future of one universe becomes the Big Bang of the next. Yet without light or any other information beyond our horizon, these remain elegant mathematical possibilities, tested only by their indirect implications for what we can observe within our cosmic bubble. The edge of the observable universe, therefore, is not just a scientific concept, it is a philosophical one. It defines the ultimate prison of perception and the frontier of curiosity. Every moment of human history, every emotion, every discovery has occurred within this tiny shimmering window. We are beings made from the remnants of ancient stars, as famously articulated by Carl Sagan, living in a universe vast beyond imagination, yet gifted with the capacity to map its origins and comprehend its boundaries. The horizon challenges our understanding of reality, existence, and our place within it. The observable universe is not the end of existence, it is simply the limit of what we can currently see and know, a horizon that recedes as we advance. Beyond it lies the unknown, filled with questions that may forever remain unanswered, and possibilities that fuel our deepest scientific and philosophical inquiries. Perhaps one day, as Michio Kaku and others speculate, new physics or phenomena like quantum gravity or subtle imprints in the CMB may offer indirect clues about the nature of the unobservable. For now, we stand on the shore of a cosmic ocean, listening to the echoes of its creation and gazing with wonder into the infinite dark, reminded that the greatest discovery may be the realization of just how much there is left to discover.